In Chapter 8, we will use the basic concepts of the sampling distribution and inference to develop intervals around a sample statistic. We'll consider two different cases for sample means. First, where we know the population standard deviation. Remember, the basis of sampling. A point estimator of a sample cannot be expected to provide the exact value of the population parameter, but we can develop an interval estimate around that sample statistic by calculating a margin of error around the point estimate. We can then provide information with some level of confidence about how close that point estimate is to the population parameter. If we are considering the sample mean, x bar, we would develop an interval estimate by adding this margin of error around. In order to calculate this margin of error, we need either the population standard deviation or a sample standard deviation. The calculations are slightly different for the two cases. We rarely know the exact population standard deviation, but frequently we have some past data from which we can make a good estimate. We will now explore this case of population standard deviation sigma known. Looking at this diagram, we introduce a new value alpha, which we'll call the level of significance. If we put alpha over 2 as the area or probability at either tail of the normal distribution, we can state that 1 minus alpha is the area between those two limits. We will call this 1 minus alpha the confidence level. Looking at this diagram, if we take multiple samples from the population, this sampling distribution of the means will be normal. We know that its mean will be the population mean, mu. If we calculate a confidence interval around each of those sample means, we can be confident that 1 minus alpha percent of the sample's confidence intervals will include the population mean mu. This is the basis of confidence intervals. We can calculate that confidence interval for the case where we know the population standard deviation sigma using this formula and a value from the z distribution. The calculation inputs include the sample mean x bar, the population standard deviation sigma, the sample size n, and this z value for the significance level alpha over 2. In defining a confidence interval, we always add and subtract this margin of error from the sample mean. Note that this formula includes the formula for the standard error of the mean from Chapter 7, which is sigma divided by the square root of n. Most frequently, we will use confidence levels of 90, 95, or 99%. This is a convenient table showing the z values for alpha and alpha over 2 for those three confidence levels. But it could be that we want it to be 97% confident or 93% confident. If so, we would simply look up those values of alpha over 2 in the z distribution table to find the area. If we assume a confidence level of 90%, the significant level alpha is 10% and alpha over 2 is 5% or 0.05. For this, the z value for alpha over 2 will be 1.645. Therefore, we would be 90% confident that the interval will include the population mean mu. Let's do a real example. Consider a sample size of n equals 36 that has a sample mean x bar equal 41,100. We assume that the population is not highly skewed and that the population standard deviation is 4,500. We do not know the population mean. We want to calculate a confidence interval at this confidence coefficient of 95%. Using the formula for the margin of error and the z-value for alpha over 2 of 1.96, we find the margin of error to be 1,470. Therefore, at 95% confidence, our margin of error is plus or minus 1,470. So adding that value to our sample mean gives us that interval, 39,630 to 42,570. We are 95% confident that that interval contains the population mean. If we repeat this calculation using different confidence coefficients, we see that we will get different margins of error. You can see that as you increase the confidence coefficient, the margin of error gets wider, therefore a wider confidence interval. In other words, to be more confident, you need a wider confidence interval. For most cases where the original population is known to not be highly skewed, a sample of 30 is sufficient. The more normal the population is known to be, the smaller the sample size we can get away with.